I want to welcome you to another statistical class. Of course, before I get started, um, I'm actually going to say for those whose assignments have not been graded, probably for assignment one, of course, um, they're going to be graded. Of course, they're going to see their results latest Saturday. Okay, I just want to tell you that the MITs are working around the clock to make sure, they get the grading done. I want to welcome you to another statistical topic. And you know what? I need you to pay more attention because what we want to do today is very, very crucial. Uh, you know, the reason why we're able to do what we do in research, in statistics and research world in general, is because of this particular topic. And I need you to pay attention. So I welcome you to sampling distributions. This is chapter 7. In the outline, I'm going to introduce you to sampling distribution. I'm also going to differentiate between sample statistic and population parameter. You remember I've walked you through this before. We are probably in chapter 1 or chapter 2, where we differentiate between statistic and parameter. I think I gave you assignment on that. I remember. So the two of them play major role in sampling distribution, and that's why we break them in. Then I'm going to also visit sampling distribution of proportions and sampling distribution of means. Like I said, you need to sit back, listen. If you have any question, you ask. Okay, let's get started. Okay, so because there's a connection between parameter statistic and inference, I want to have a recap on that so that you'll be able to see the connection these have with sampling distribution. Now, let me tell you this. Parameter is anything that's any information we're seeking to get. I remember I said parameter is a population characteristic value. Whatever things we have in mind that we want to figure out, that's what we call parameter. Parameter could be what is the percentage of the citizens that approve the job the president is doing. Parameters could be, on average, what is the numbers of hours the students of University of Minnesota commit to studying? Parameters could be, what is the average household income in a country? Okay. Parameter could be, what is the rate of prevalence of a particular disease? So the bottom line, whatever we have in mind to figure out, whatever information, whatever, things that we have in mind that we're seeking to determine is what we call parameter. Now, and if I were to get parameter, I need to go to population. I'm going to say that again. If I want to get parameter, if I want to get the exact value of parameter, I need to go to population. But you know what? We are limited by budgets. We do not have resources to study everybody in the population. What do we normally do? We take a sample. So when we take a sample, what we obtain from the sample is what we call statistic. Okay? Okay, what we obtain from the sample is what we call statistic. I'm going to give you a funny example that I normally cite. Like, let's say my wife is cooking in the kitchen, and maybe the aroma from what she's cooking is actually disturbing me. And I say, okay, oh baby, can I have a taste? Like, I don't need to eat everything in the pot before I know how it tastes. What I'm actually going to get from that regard is going to be a sample. When I put a sample in my mouth, okay, whatever I deduce from the sample is what we call statistic. But do you know what I want initially? I want parameter initially. Parameter is, and before I can get a parameter exactly, then I need to eat the whole pot of soup. That's not visible. And that's why doctors normally extract a sample. They don't need to extract the entire blood, blood in the bloodstream of patient before they know what's going on. Now you understand parameter, you understand statistic, and you know what? What we want to do today, which we call sampling distribution, we enable us to use our knowledge of the statistic to generalize on the entire population, trying to figure out the parameter. I'm going to say that again. Sampling distribution will enable us to use statistic that we got from the sample to be able to generalize to the entire population, so that what we're trying to say, that statistic will be used to represent parameter. So what we enable that is sampling distribution that we want to do today. But you know what? Before I go into the problem, I'm actually going to give you maybe I should give you significance of sampling distribution. What is the relevance of sampling distribution to scientific community, to research world in general? And I need you to listen now. Number one, it enable estimation of parameter, which means we'll be able to estimate the parameters that we want. Estimation is just talking about, I'm going to use my knowledge of the sample. Does that make sense? Sampling distribution allow that. So the sampling distribution enable us to estimate the parameter that we want. Does that make sense? That is one of the significance. I'm still going to walk you through the sampling distribution. I'm just trying to prepare your mind, trying to give you that. Number two, you know what sampling distribution that we want to talk about do? It will allow statistical inference. I'm going to say that again. Sampling distribution provide foundation for statistical inference. What do I mean by statistical inference? Statistical inference is about generalization. So sampling distribution will actually provide that foundation upon which I can generalize whatever I get from the sample on the entire population, which is crucial for statistical inference. Okay. Subsequently, we're going to walk you through a topic called confidence interval and hypothesis testing. Without sampling distribution, no way. There's no way we're going to have that. So when we talk about statistical inference, we're talking about generalization. Does that make sense? Sampling distribution enable that. Sampling distribution also allow us to use the idea of central limit theorem. Okay? I'm going to tell you how central limit theorem works. The central limit theorem, we believe when we take large samples, the statistic will converge to parameter. Take a look at that. Don't forget, we want to use statistic. Where do we get statistic from? From the sample. We want to use statistic to represent the parameter because it is very expensive and may not be visible to get parameter exactly. Because if you want to get parameter, you need to study everybody. We don't have time for that. We're limited by budget, and that is what we mean. And I'm also going to say with the sampling distribution, okay, we have a measure of variability. Okay, variability and precision around statistic, because we know statistic varies. And I'm going to show you why statistic varies. But you know what? Statistic that varies, okay, sampling distribution enable us to measure variability around that. And how do we measure variability around that? It did that by means of standard error. I'm going to also unfold all of that to you. And lastly, sampling distribution. This is the most important significance. Listen now. Sampling distribution will facilitate our understanding, okay, of how statistic varies from sample to sample. Statistic varies. And I'm going to show you why statistic itself varies. Okay, but you know what? I'm going to start with a problem. Okay, and the problem I'm going to start with in the approach in the chapter that we want to start today, normal distribution is very crucial. You remember in the last chapter we talked about normal distribution, how to assess normality, and I told you we normally celebrate if data set follow normal distribution. Why do we celebrate? Because normal distribution, when data set follow normal distribution, that will facilitate easy computation of probability. Therefore, the idea of a normal distribution will be in use in sampling distribution. Now, I want to start right now. I need you to pay attention right now. We got a problem. And what is the problem? We talk about normal distributions the other time, and whenever you want to use normal distribution, the assumption in the last chapter, you're actually going to be given the two parameters, right? That was assumption. Because we're always going to be given the mean, and you're also going to be given the standard deviation. Those are the two parameters. But let me tell you, in a real life, practical situation, those are unknown. Does that make sense? In the last chapter, when you want to work with normal distribution, we give you what? We give you parameters, right? We give you the mean, we give you the standard deviation, then we ask a question, right? But in that regard, we're assuming that they are known. But in the real sense, in the real life, they are unknowns. And if they are unknowns, what is going to happen? If they are unknowns, what is going to happen? We cannot get them exactly. The only way to get them exactly is actually to study everybody. We don't have resources for that. We're limited by budget. What are we going to do? We're going to take a sample, right? When we take a sample, we estimate them. Does that make sense? We estimate them. So, and that is what I'm trying to say here. Okay. Okay. They are unknown. Okay. Then we're going to estimate them. Instead of us to have a population mean, you know what we're going to have? Sample mean. Instead of us to have a population standard deviation, what are we going to have? Sample standard deviation. Does that make sense? Because what we have at our disposal is sample. Now, I need you to pay attention now. Okay? Now, we are in election season or period in the United States. Okay? I told you the other time, as human beings, we want to secure our environment, we want to secure political environment, we want to secure our medical environment. Now, let me talk about political environment now. In United States right now, where they are preparing for presidential election, supporters of a particular candidate, they will be curious. They really want to know what is going to happen. And because of that, we got some cable channels or some posters that are conducting surveys where they ask, for example, take a look, let's say if you take a look at example 7.1 now, let's say the parameter is we want to know the true proportion of America that approve the job the president is doing. The parameter is P. We want to know the proportion or the percentage of Americans that approve the job the president is doing. If I want to get that exactly, I will need to study everybody in the United States. Does that make sense? I will need to investigate that. But you know what? Because that would be impossible to do, okay? Because we don't have time for that and we're limited by budget. And because of that, we may not be able to get the true approval rating. Don't forget, the true approval rating is a parameter. Then what are we going to do? Now, station like ABC, oh my God, the ABC is actually a news cell channel in the United States. They actually pull 1,000 adults randomly, and they ask them question, is the president doing okay? That was a question. They actually expect response yes or no. They count the numbers of yes, and they realize 512 approve the job the president is doing. Now, because we're making use of sample, oh my God, we're making use of sample, then you're actually going to see a cap on P. When you see a cap on P, that's an estimate of the proportion. P without a cap, this guy here, is the population parameter, which we call which is a population proportion, the true value. But what the ABC is giving now, okay, this is the intelligent guess by ABC about the proportion of Americans who approve the job that the president is doing. You know what happened? Another organization decided to go into American population, choose a sample size of 1,000, and they got that 485 approved the job the president is doing. And they estimate from the CBS now is conflicting. Oh my God, is conflicting with the estimate of the ABC. Now let me tell you this. If different organizations should go into a United States population and take a sample because they are not using the same sample, they're actually going to get different results. Not only in the United States population, when you are taking a sample from a population, for instance, this is what happened. Let's say I want to give each of you assignment, and I say, okay, what you need to do, go to the university of this university, select 50 students randomly and ask them whether they actually love sports, for instance. Some may love sports, some may not. Maybe one of maybe that person there interview 1,000 University of Minnesota student, and I know the result is going to be different from if another person should go into the same population and choose the same sample size randomly, they're all going to get different results. Because of that, statistic is a random variable. Does that make sense? Why do I call statistic a random variable? Don't forget, statistic is what you get from your sample. You're getting different results. So what I'm trying to say now is 0.512 is 0.485. And even if CNN should go and do the same, if others should go and do the same, they're actually going to get different estimate, okay? And that is to show you that statistic varies from sample to sample, taken from the same population. And you know what? Sampling distribution is what is going to enable us to see how the statistic vary. Because when I say sampling distribution, it means I'm conducting a repeated repeated experiments. Because if I ask, they are conducting, this is more or less like a repeated experiment. ABC go for one, CBS go for another one. And you know what? If a good number of them should go and we have different results, then it means statistic varies. Now the question is, which of the results should we trust? Okay? Is it the one from ABC? Is it for one from CBS? And that is the reason I remember what is going on right now in the United States, where they said, this is the chance of this president, of this candidate, this is the chance of this candidate. Different pollsters release different results. And you know what they're going to do at the end of the day? They will average them. Average from the result of all polls. Okay? But before we can average them, we need to first know possibility. We need to know possibility. So the sampling distribution now enable us to know possibility of what the value of statistic is going to be. Now that the value of statistic is a random variable, then we can begin to look at the probability distribution for it. If it is normal, okay, then we're going to find the average. And that is why you normally see when they release result of different polls, CNN polls, New York, Olympia. I think there are so many polls, for election in the United States. And at the end of the day, they will find the average. But before they can find the average of all polls, they have to follow normal distribution. Now, what sampling distribution will enable us to know the possible values statistic can take with their corresponding probability. Because there will be some group of posters that have the same value as a ABC. There's going to be some poster that also have the same value as this. And that is why frequency is going to come in. How many of the posters actually got this result? How many got this result? How many got this result? Now sampling distribution is trying to say, what is the possible values statistic can take with a corresponding frequency? That's what we mean. Now, you know what I'm going to do? I'm actually going to use candies now. You all like candies, right? Okay, now I need to take a look at this. I got candies with different colors: orange, brown, and yellow. I'm seeing these three as political candidates. When you take, maybe I go into the population. When I go into the population, I need you to listen. I need you to listen. If you don't understand, ask question. I go into the population. I go into the a big bag. I put 50 orange candies, 50 brown candies, 50 yellow candies. I mix them together. I want to ask a question. What is the distribution? What will be the distribution? I put 50, 50, 50. I put equal. Can somebody tell me? What will be the distribution? You saw what? Okay. Thank you for sharing. Very close. You saw what? Oh my God, it's uniform distribution. Send me a message for extra credit. Why is it uniform? Because they have the same number. Which means population is not normal, it's uniform. But do you know, when we do something, statistic from it will be normal. Even though the population is not normal, statistics from it will be normal. And I want to demonstrate that to you now. Okay. Now, do you know that if I give you assignment, okay, and you know what I need you to do, you can do that on your own. You can get some candies, different colors like this. Okay. Put them together. Okay. Now you know what I needed to do. Maybe I'm actually going to say, maybe pick 20, pick 20 randomly, report the number of orange, okay, report the numbers of brown, report the numbers of yellow. Maybe what I'm interested in is yellow, okay, and I ask every one of you to do it. The numbers of yellow you will each report will not be the same. Does that make sense? Why is it that it's not the same? Even though you are selecting the same sample size, don't forget you are choosing at random. The numbers of candidates in my sample cohort will be different from the no, I'm sorry, the the composition of the candidates in terms of color in my cohort is different from you. It's not from your own. And that is the reason why if ABC should go out and sample the opinion of people, if ABC choose 50 Americans, CNN choose 50, they all choose the same number, then we have different statistic because they are choosing randomly. Because they don't have this, they don't have that same participants, even though they have the same number of participants. Does that make sense to everyone? That's what I'm trying to say here. But you know what? I will quickly move to, so what I'm trying to say here is, okay, when I ask any one of you to do this, what you're going to report here will not be the same in terms of how many candies for yellow, how many candies for that, then in terms of proportion. Go ahead. Exactly. Yeah, but we're not yet there yet. We got condition for attaining normality because that normality now will depends on the sample size that we choose. Does that make sense? We are still getting there. But what we're trying to say initially, the population is not normal. Okay, now I'll quickly show you a website because what we want to do, we want to compare sample statistic to the population. Don't forget the other time, we want to represent population parameter with sample statistic. But before I can use this a particular sample statistic to represent the population parameter, we need to be able to see whether that very sample statistic will make a whole lot of sense. Does that make sense? Now, because of that, I'll quickly go to a website. Please take a look at this. There's a particular website, okay? And in that website, you're actually going to see a lot of candies. Okay, it is called recess pieces. Now, you ask a question at that time, right? If you take a look at that, there's a lot of candies. They are in equal number. The number of yellow is the same as, but you mix them together. And you know what happened? They maybe one, I asked, you know what? Go into this pool and pull 25 candies. 25 candies. Okay. Now somebody may report this. If you so after taking them, the 25, you now separate them by colors. So that is for one person. Okay. Now that is 0.48. Maybe I'm interested in let's see. Maybe I'm interested in what is it? Yellow? Oh, sorry, brown. Or what color is this? Yes, yes. Okay, I talk about orange or brown and okay. If I'm interested in this color, okay, one person is say, okay, I got 48%. That is for one person. Okay. But you know what I said? You know what I did? I said 300 persons should go. Look at that, 300. Number of samples is different from sample size. Let me do this. If one person should go into the pool 300 times, at each occasion, choose how many? 25. Okay. It is the same as 300 people go once. Does that make sense? That is what we call sampling distribution, repeated. Does that make sense? Now, you know, for 300 people now, for 300 people, they're actually going to have different proportion, which is what you see here. Which is what you see here. What are we trying to do now? What we're trying to do now, because the statistic varies, we can draw histogram. We can draw some plot to be able to see whether it follows normal distribution or not. Oh my God, look at that. Now, what is it trying to say now? This is like a normal shape. Okay, take a look at that, right? You see that? Oh my God, initially, the population was uniform. The population was not normal, but what happened? The distribution of the statistic now is normal. You know what? What we want is for the distribution of statistic to be normal so that we can use normal properly because of simplicity. Go ahead. We did not deliberate make the population to be uniform because in real life, the population can be normal or not. Okay? But what we want at the end of the day, because we know statistic varies, we are interested in the distribution of the statistic. So what are we going to do? To make the distribution of the statistic to be normal, then we have to take a large sample. So what we're doing now, so the last sample here is 25, because you know why? If you choose 5, if each and every person should go to the population and choose just 5 candies, okay, and you plot the graph, it's not going to be normal. So the more sample we take, then the more the distribution, okay, approximate normal. But let me tell you this. What if initially the distribution is normal initially? If the distribution is normal of candy is normal initially, whatever we do, even without doing nothing, the distribution of statistic will be normal. Does that make sense? If the population distribution is normal, automatically the distribution of statistic will be normal. But if the underlying distribution is not normal, then we need to choose a large sample before the distribution of statistic will be normal. And who says that? What theorem says that? That's central limit theorem. So central limit theorem in statistics states that even if the underlying probability distribution is not normal, when you take a sufficiently large sample, the distribution of the statistic will be normal. Does that make sense to you now? And how large is it large? How large is it large? Okay, the agreement, it should be 30 or more. Okay, 30 or more. Okay, but here you can see 25 still work, because if it is normal, it will be easy to find the mean. It will be easy to find the mean. Does that make sense? And the mean is going to be Sarah. It will be easy to find the mean. It will be easy to find the number of standard deviation. Now, I need you to pay attention now. When the mean, you know, the Sarah, For statistic, it's like mean of the means. Don't forget statistic itself. It's like a mean. Each of that is like a mean. You now find the mean of the mean. That is the center. And for you to find the mean of the mean, the distribution has to be normal. What will be the movement? What will be the deviation away? The deviation away from the center here, we don't call it standard deviation. We call it standard error. Look at that. Okay. When I'm working with just random variable and I have a normal distribution for random variable, okay, deviation from the center is called number of standard deviation. But right now, I'm working with statistic. Okay. So if I want to measure variability around statistic, the movement is called standard error, not standard deviation, standard error. Okay, now I'm going to move right now. Please pay attention. I'm still on that website. Okay, this is the population of Candice with colors. Somebody go into this and choose a sample size. Okay, the person got this. Another person, okay, go all the way. Another person, choose sample size. We got this. Or it may even be you that you are visiting so many times. You visit first time, you got a 0.44, second time, third time, all the way, you get different values. Then what do? You now do what? You generate the histogram. What do you see? Normal. Do you see that? That's exactly what we want. Okay, now I need you to pay attention now. What is the takeaway from what I've explained so far? Sampling distribution will enable us to see how statistic varies, okay, from one sample to the other. When I say statistic, it could be proportion, it could be mean. Now, let me ask you this question. Like if I ask you to go into the University of Minnesota population, and I said, choose 50 students at random and calculate the average height. The average height that you're going to have will be, each of you will have different average heights because you are not using the same students. You are choosing 50 at random. What happened? You have several means, right? I got my mean, you get your mean. Mean now become a random variable. Mean is a statistic. So what are we going to do at the end of the day? Then for us to be able to know what measure, I have several means. Should I find the mean of the means? Or should I find the median of the means? Or should I find the mode of the means? You know what we answer that? What we answer that is the distribution. If your distribution is normal, then you find the mean of the means. If your distribution is not normal, you can find the mean of the means for the average. So distribution in statistics is very, very important for us to be able to know which measures that work. Does that make sense to everyone? That's why we're doing what we're doing right now. Okay. Now I needed to take a look at example 7.2. A roulette wheel in Las Vegas has 38 slots. 18 of 38 numbers on the roulette wheel are red. Another is time to play the roulette, then the bet is money on red. Now, a bet is money on red. He has the characteristics of interest is red. That's what he has in mind. Does that make sense? Because you bet on red. Okay, the probability distribution of the output is given as this. Please, I needed to pay attention. Okay, the probability of winning, W, that is 9/19, and the probability of losing is 10/19. I needed to take a look at what we have here. Okay, now if you have this one now, okay, the next thing is Adam will play 2 games. Okay, list all possible outcome for each outcome, then calculate the P cap, the proportion of winning. It's going to play 2 games. Since it's going to play 2 games, there's going to be more than one possibility. The first possibility, it could lose the first and the second game. It could lose the first and win the second game. It could win the first and lose the second game, or it could win both. Take a look at that. There's a possibility. Those are elements in the sample space. Now, but if you take a look at this guy, okay, now winning both game, sorry, losing both game, the pickup equal to 0. Winning one of the games, 1/2. And winning both game, 2/2. Now, when you take a look at what I have, we actually are talking about different statistics that could come up. It could lose both game, it could win one of that, and it could actually win both. Now, when you take a look at this now, the sample statistic varies. What could be the the sample statistic varies, and that's exactly what we see. Now, if you take a look at this one now, it said use a part A to find the sampling distribution for sample proportion p cap. Now, if I want to use the idea of a sampling distribution now, okay, p cap equal to 0. Okay, now the p cap equal to 0 is the same thing as the probability of L intercept L. L intercept L, like the first the joint probability of losing both games. Now, and you remember what we did before for independent law, the probability of the joints, okay, here we are assuming sampling with replacement, right? That's why you have 10/19, 10/19. Don't forget the 10/19 is actually here. They've given you a probability of losing 10/19. So you just multiply that, okay? And at the end of the day, okay, you actually have this guy. Now, the probability of this guy now, that the p cap is going to be equal to half. Now, let me tell you this. This guy here is trying to say, what is the probability that your statistic, which is the estimate of proportion, will be 0? Okay, don't forget, statistic become a random variable. The statistic here is a random variable. So the probability that is going to be equal to 0 is when it lose at both ends. Lose the first game, lose the second game. And that probability is this. That probability is that. Now, the probability that's going to be equal to half, and you remember the other time I said equal to half, okay, is this condition. Winning the first game, losing the second one. Or losing the first game, winning the second one. Okay, and all what you're going to do here is to do the probability of W intercept L, and you also do the probability of L intercept W, but when you do it once, you can multiply by 2 because they're going to be the same. Now, you can also find the probability of P cap equal to 1. Okay, so P cap equal to 1 actually means you're going to win at both sides, which is this guy. So which means here, what you're going to do here now is, what is the probability of winning first, intercept, winning second? Don't forget, what is it going to be? It's going to be the product, probability of W times probability of W. Okay, do you understand that? Now take a look at this now. Because of that, based on what I've done here, okay, I said here you're going to find the probability of L intercepts W. Okay, and you know what? The probability of L intercept W is the same thing as probability of W intercept L. Then I can just multiply this guy by 2. Okay, whatever I got. So the result that I got here, you know what I'm going to do now? I'm going to create a table. I need you to pay attention now. The table here, is not the same as the table here. The table here is for the population, the way it was. Does that make sense? The table here. But the table here now, you have considered statistic to be a random variable where when statistic equal to 0, when statistic is equal to half, when statistic equal to 1. And you now find you have been able to compute the corresponding frequency. You know, for when p cap equal to 0, I got 10, I get 100 over 61. When p cap equal to half, okay, you are, so what it's trying to say, when you follow what I said, you're going to get 180 over 61 over 361. When p cap equal to 1, where you actually apply this guy, where you multiply the probability of W times probability of W, that is actually going to give you this guy. And you know what I have here now? Please pay attention. Please pay attention. This guy is probability distribution. This guy. But this guy is sampling distribution. There's a difference between probability distribution and sampling distribution. The probability distribution is the distribution of your data set initially, the distribution of the population. And after you are done with your statistic, what you have now is sampling distribution. You know what this guy is trying to tell me now? Okay, I'm able to know the possible value statistic can take. Statistic can take 0, statistic can take half, statistic can take 1. Not only that, it also provides me with information about their corresponding frequency. Does that make sense? And that is what this guy is trying to talk about now. Okay, now, do you know, if I take a look at this distribution and I realize it is normal, if it is normal, then what I'm going to do, I can find the average. Now, if I want to find the average, what am I going to do? Oh my God. You know that I've already given you an approach before where you're going to multiply this by that, you're going to multiply this by that, you're going to multiply this by that, and you're going to add them up. That's exactly what we're doing here. But you know what? If the distribution is not normal, if the distribution of statistic is not normal, we cannot use this approach to find the mean. Now, I need you to pay attention now. Okay, look at this notation. What is it saying? Mean of the sampling distribution of statistic. Mean of the sampling distribution of statistic. What statistic are we talking about? Proportion. That's why you say mu p cap. And that gives you that. If that gives you that, oh my God. If we want to get the variability now, or we want to measure precision now, then we can also talk about the variance. You remember we did something like that. Then finally, you get the standard deviation. Take a look at this guy now. Whenever you are dealing with statistic, that guy is not standard deviation. But you know what we're going to say? It is a standard error. And we normally put it this way. Standard error is the standard deviation of statistic. I'm going to say that again. Standard error is the standard deviation of statistic. You can say I mentioned statistic, right? So that is what we have. You know what? I'm going to stop here today. I'm going to continue next time. Make sure You all stay safe and have a lovely weekend. Bye for now, everyone.